Okay, so yeah, so today we'll discuss problem on these are based on week 12 content. So this actually deals with the you know designing using the state space approach. So we already have seen like how to design, that is basically we want to achieve some kind of criteria, for example overshoot or settling time of a our system or plant. So we want to design a controller to achieve that. So we already have seen that in the frequency domain. So in the frequency domain, what we do is that we actually design for the dominant poles, right? So we place other poles such that it will not affect the, you have a will have a dominant poles, and others pole zero effect will be very negligible, or they may cancel with each other, something like that we did in the frequency domain. So in the time domain, so we have uh, we can place all the poles, not only the dominant poles but all the poles arbitrarily as we want. So if the system is completely state controllable, so that is one necessary and sufficient criteria for placing poles. So using some suitable feedback controller, we can place our poles arbitrarily, and we know that depending on this pole, our system will response will, it will be determined by this pole location. So in some sense we are just controlling the behavior, but we will verify that also using some kind of simulation, for example MATLAB, to whether we have achieved or not. But the first step of design is that we we decide where to place the poles of the system. So then we choose our control, that is actually in the feedback form, that is a proportional to state. So then we choose this gain matrix as k, such that we can place our poles at the desired location if the original system does not have that poles in that particular location. So we see that we need our state for designing that control law. So in some cases we may not have access to all the state variables, then we need to estimate them. So that's how the observer concept comes. So we estimate our state from the control sequence that we already know, and from the output that are function of the states. So the output will be dimension will be very smaller as compared to state. So we may not like instantly determine them, but over a period of time we can determine the state, and that's how the observer design is there. And then using that estimated state, we use the controller design to achieve our to place this pole in the desired location, or to achieve some other criteria also. Okay, so we'll discuss this. So we'll discuss only basic problem here. So we'll start. Okay, so the first problem, so it's very simple. So we have a given a state space representation. So we want to just find the eigenvalues and the eigenvector corresponding. Okay, so that will help us to in other designing process, or to compute the state transition metric and so on. Okay, so first to find that, so what we will do, we'll just find the eigenvalue. So find the eigenvalue, it's simply this, we just make this determinant equal to 0, then we compute this eigenvalue. So this is the A matrix for that state space representation. So then we see that it's lambda minus 1 minus 5 0 lambda plus 1 determinant equal to 0. So it implies that lambda minus 1 into lambda plus 1 equal to 0, or eigenvalues are plus minus 1. Then to find the eigenvector, what we do, we just see which vectors make equal to 0, or simply x equal to lambda I x, or I can also write it lambda x also. So here lambda are the eigenvalue. So for each eigenvalue we just compute the eigenvector. Okay, so this eigenvector may not be unique, but they will be the scalar multiple of the basic vector. Okay, we just have to find one vector that will be or scalar multiple of that will be, any scalar multiple of that vector will be eigenvector. Okay, so just we'll do that. So then first is for lambda equal to let 1 value, so we just compute that. So then we just put in this equation. So we have 1 5 0 minus 1. So we have this x1 and x2, so we have to compute that, the eigenvector value, and 1 multiplied with x1 and x2. Then we just equate both sides, so we just simplify this. This is x1 plus 5x2, this is minus x2. Okay, so this equal to x1 x2. So we see that minus x2 equal to x2, so that means minus x2 equal to x2, or imply that 2x2 equal to 0 or x2 equal to 0. And from the first condition, it is x1. So because x2 already have 0, so x1 equal to x1. So we see that x1 for any value it will satisfy. So we can choose x2 0, and x1 we can choose any scalar multiple of 1. So this will be eigenvector. So any value like 5 0 2 0, anything can satisfy, right? So we just choose this one, and any scalar multiple of this vector will be the eigenvector. So this is at lambda 1, then this is the p1. Similarly, for the second case we will again use that. So lambda equal to minus 1, then again we just write this equation again. This is the eigenvector equation, x equal to lambda x, or imply that we have 1 5 0 minus 1 x1 x2 equal to minus of x1 minus of x2, because lambda is minus 1 here. So then we see that minus x2 is x2, you can simplify x1 plus 5x2, and this is minus x2 is equal to minus x1 minus x2. So we see that second condition is trivial, minus x2 is x2, and the first condition we see that, okay, so I'll use here. Okay, so first condition is x1 plus 5x2 equal to minus x1, or imply that 2x2 x1 plus 5x2 equal to 0. So I can choose x1 x2 such that this equation satisfy. So one particular choice will be like I choose this is minus 2 5, or I can choose 2 minus 5, and so on, any scalar multiple of that. So we see that 5 minus 2, and any scalar multiple of that will be the eigenvector for that particular eigenvalue minus 1. So you see that which of the scalar multiple is present there, and you see that 1 0, or any scalar multiple also, or here also any scalar multiple of this p2 vector will be the corresponding eigenvector for this eigenvalues. Okay, so just simple question. Okay, so anyway, so we move to the next question then. Okay, so for this is just simple question, so you just find the eigenvalue and then the eigenvector. So this just follows directly from the definition, you just have to solve them. So then we see that, okay, using that eigenvector, we already have seen how to compute the state transition matrix in the previous live session, so we'll just repeat that. So what we'll do, that we have already this eigenvalues and eigenvector, so we'll just place this eigenvector p1 and p2 as the column vector of the p. So 0, this is 5 minus 2. Then we, if we use the similarity transformation, then we can diagonalize this matrix. So diagonalize this matrix means this matrix will have only the eigenvalue in the diagonal element, and other element will be 0. So this diagonal matrix will be what? So this will be, this eigenvalues are this. So for this we know that easily we can compute this state transition matrix when this matrix is a diagonal matrix. So this is just e to the power t and e to the power minus t 0 0. So what we do, if the diagonal matrix is lambda 1 lambda 2, so these are the eigenvalues of the matrix, then the corresponding state transition matrix, sorry, e to the power dt will be just e to the power lambda 1 t, e to the power lambda 2 t. So this eigenvalue will be raised to the exponential power, and all the other element, the off diagonal element will be 0. So that's how we can compute the state transition matrix for the diagonal matrix. But we want the state transition matrix for the original matrix A. So how these are related? So this state transition matrix of the original matrix is related to the diagonal matrix state transition matrix by this formula. So once you know this, so this is easy to compute, because this eigenvalue, once we know the eigenvalue of the A matrix, we know this diagonal form. From that we can easily compute this state transition matrix for that particular diagonal matrix. But once we compute the state transition matrix of the diagonal matrix, then we just have to multiply this P matrix, which is the eigenvector matrix. Then we can compute the state transition matrix of the original A matrix. Okay, so for that then we need P inverse. We already have P, so we compute this P inverse. So P inverse is adjoint of P by P determinant. Okay, so P determinant, we can here compute this P determinant. It's simple, minus 2. This is 1 into minus 2, 5 into 0, so minus 2. So it's 1 by minus 2 or minus 1 by 2. Then the adjoint of P for 2 cross 2 matrix, it is easy to compute. So what we do, we just switch the diagonal element. So 1 and 2 will switch this place. So this will be minus 1 and 1, and the off diagonal element, that is the 5 and 0, will be written with minus sign. Okay, so this is the adjoint matrix for the P matrix. So then P inverse is just, this is 1, 5 by 2, 0, minus half. Okay, so this is the P inverse matrix. Okay, so this is okay. So then we just substitute this P and P inverse and just simplify that. So P is 1, 5, 0, minus 2 e to power dt. We have computed it. This one e to power t, 0, 0, e to power minus t, and this is 1. P inverse is 1. This one we have computed 1, 5 by 2, 0, minus half. Then we just simplify that. So this is 1, 5, 0, minus 2, and this is e to power t, and 5 by 2 e to power t. This is this 0, and this is minus e to power minus t by 2. And if we just simplify that, then we get this state transition matrix, e to power t, 5 by 2 e to power t minus e to power minus t, 0, e to power minus t. So this is the state transition matrix of the original A matrix. So this is e to power at. So we see that we can compute directly using the diagonal form. So just to recollect what we have done. So what we have done is that this diagonal form of the matrix, if these eigenvalues are distinct, then the diagonal form of the matrix is simple. You just have these eigenvalues in the diagonal, and its state transition matrix for the diagonal matrix is simply, we just raise it to the exponential power here in the diagonal element and keep this off diagonal element 0. Okay, so then the state transition matrix of the original system, the A matrix, is related to this diagonal matrix by this relation. So here P is the eigenvector. Okay, so eigenvector, all these eigenvectors are stacked column wise. So we have this two dimensional case, we have two eigenvectors P1 and P2 that we have computed here. Okay, so we have computed this P1 and P2 here. So this P1 and P2, we stack them to get this P matrix, and then using this formula we can easily compute the state transition matrix of the original matrix. Okay, so we have already discussed this also in the previous session, so this is just a repetition of that. Okay, so then we come to whether that system is actually, the system, we already have this, so whether this system is stable or not. Okay, so again that without any control means you put this u equal to 0, then your system is what? So your original system was this x plus bu. So when u is 0, it is just this autonomous system, and for that that it will be stable or unstable will depend on the eigenvalue of the A. So we already computed this eigenvalue for this. These are 1 and minus 1. So we see that these eigenvalues are also the closed loop poles, right, for this system. So we see that one eigenvalue is positive and one is negative. So for this positive value, the system will be unstable. Okay, because it is present in the right half plane. So this system is actually unstable. Okay, So then we move to whether the system is controllable or not. Okay, so the first question is whether the controllable means whether we can choose our control arbitrarily to place the pole of the system at the arbitrary place or not. Okay, so or in terms of controllability means in the state space, it means that whether we can drive our system from a given state to a particular desired state using one unconstrained control in some finite time. Okay, so this is the controllable definition. So for that one easy way to check is this heavy. So it's for 2 cross 2, we just terminate this controllability matrix here. Whether this controllability matrix is a full rank, that means its determinant is not equal to 0, then it is controllable. Okay, so we see that then what this controllability matrix. So this controllability matrix, so B is 1 0 and AB will be what? So A is 1 5 0 minus 1 and B is 1 0. So if you multiply that, it's 1 and 0. Okay, so this is C matrix. So you see the C determinant is equal to 0. So we see that it's not full rank, so the system is not controllable. Or you can easily also check from this representation. So from this representation we just write then what is this, x1 plus 5x2 plus u and x2 dot equal to minus x2. Okay, so you see that for x2 variable there is no effect of u control, right? Because it's just depend on x2 derivative, just only depend on x2, it does not depend on the x1. Okay, if it depends on the x1, then through x1 you can affect this x2, right? But here you see that it's just an autonomous system for x2, that x2 derivative is x2, so it does not depend on the control. So using this control you cannot actually send your x2 to a arbitrary position. Okay, so in that form also you can see that this system is not controllable. Okay, so fully state controllable. So the first question is the system is controllable, so either by this controllability matrix or by this form. So you see that this is in the controllable canonical form already. So instead of this in the controllable canonical form, what we have, so it is like in this form, right? It will be some minus a1 minus a2 like this. Okay, so one system will be decoupled and the other will be like this form. Okay, so it's not exactly that, but it is decoupled in the x2 variable. Okay, so you can see by just expanding that also. So from this also we can conclude that x2 variable or x2 mod is not affected by the control, right? So it's not controllable, so it's not fully state controllable. Okay, so now we come to issue of stabilizable. So what it mean by stabilizable, whether you can drive your system to be a stable system. Okay, so for that, okay, so if it is fully controllable, then you can always find a control, like by definition you can find a control that can actually drive the system to 0, right? So it means that stability means your transient response should go to 0. Okay, so that you can easily do when it is fully controllable. So if a system is controllable, that implies that it is stabilizable. Okay, so this direction is always true, but the other direction is not true, that is even if it is stabilizable, it may not be a controllable. Okay, so by definition of stabilizable means whether you can drive your system to a system matrix to a stable matrix, or whether you can drive your the state to 0 using control variable. So for uncontrollable system, then what will be the condition needed? So if the controllable modes are stable, then you don't have to do any changes in there, right? But if your system is some modes are not stable, then you have to drive that to 0 by using a control. So if unstable modes are controllable, then your system is actually stabilizable. Your uncontrollable modes are stable. So you see that this x2 variable, this is uncontrollable mode, and for that you see the negative sign, that means it is stable, right? Because of the negative sign, or it is associated with this eigenvalue of -1, so it's stable mode. The unstable mode is this one, first one, that is associated with this eigenvalue 1, but because you can use your control to drive that to 0, so that you can also make this x1 to be 0, right? So this uncontrollable mode is already stable, and the controllable mode you can, by choice of control you can make it to 0. So that means your system is stabilizable. Okay, so this is stabilizable. It is not controllable, but it's stabilizable. That is, you can make your system to stable by choosing, your control. Okay, so then we come to the design part. Okay, so we consider the same state space model, but now we want to design. Okay, so we already seen that our eigenvalues or the system closed loop poles are at what, 1 and -1. Okay, this eigenvalue we computed for this previous system, but we want them both to be stable. Okay, so one choice will be like we want to place it -1 and -1. Okay, so why we choose -1 and -1? So we see that unstable mode we cannot change, right? Its eigenvalue or closed loop pole is -1. So the second one we cannot choose. The first one we can choose. This is for x1 and x2. Okay, the eigenvalues. Okay, so one eigenvalue we can choose, other we cannot choose. So we can just arbitrarily choose -1 and -1. So second one is already fixed at -1. So the first one we just choose -1. Okay, we can choose also other values for the first one also, eigenvalue. Okay, so when we derive, we will see that only one k value will actually affect this eigenvalue. Okay, so we'll just see just by deriving that. Okay, this is because the system is not fully state controllable, right? So we cannot arbitrarily place all this closed loop poles here. So if it is fully state controllable, then we can place all these eigenvalues arbitrarily. But if it is just partially controllable, then only that portion of the system we can actually choose our control to place their eigenvalues at that desired location. We cannot choose our control to place other uncontrollable modes eigenvalues, right, or the closed loop poles. Okay, so we'll see that. So we'll just use this direct approach, that is we just write this. Okay, why choose only one eigenvalue, that to the first one only. Okay, so I'll just explain. Okay, just let me finish this. Okay, then it will be clear. Okay, so what I want to say. So first I will just complete this question, then it will be clear. Okay, why we can just choose one value and the other we cannot place the other eigenvalue at the desired location. Okay, so let's first complete that. So we want by this question we want our closed loop poles at the -1 both. Okay, so then what will be the characteristic equation? So this will be, okay, so s square plus 2s plus 1. So this will be the characteristic equation for the desired pole location, right? So then we want, okay, our system was given like this, x plus bu, and we want u to be minus kx. Okay, where k is this matrix, then it will be what, a minus bk x, right? And our closed loop matrix will be this. So let's denote this a tilde. So we just compute that by putting our given data. So a matrix is 1 5 0 minus 1. So 1 5 and 0 minus 1, 0 minus 1 minus, okay, so b matrix is what, it is given 1 0. Okay, 1 0. Okay, then k1 k2. Okay, and x. Okay, this is a tilde. So let's compute a tilde. So it is 1 5 0 minus 1 minus.
Sir, your voice is not clear, sir.
Huh? Which one? Can you repeat? Sorry.
Your voice is not clear, sir.
Which is not clear? Voice. Okay. Sorry.
Now, now okay, sir.
Now okay. Can you hear?
Yeah.
Okay.
Yeah, sir.
Okay. So what we are doing is that we just will choose a control of this feedback form, that is u equal to minus kx. Then the closed loop pole will be matrix will be this a tilde, right? So we will just compute this closed loop matrix. Then we will see that we want this closed loop matrix eigenvalue to be this one, like 1 and minus 1, or this characteristic equation associated with this closed loop matrix to be this one, the desired one. So this is the desired one. So this is the step. So in the direct method, so we'll do that. So for that we first compute this a tilde, and this is just a minus bk. So we just substitute a and k. So this is what? So k1, k2, and this is 0, 0. Okay. So okay. So then this a tilde is what? So 1 minus k1, 5 minus k2, 0, and this is minus 1. Okay. So this is a tilde matrix. Then we see that, okay, so if we want to find this eigenvalues, then what we do with it? Si minus a tilde determinant equal to 0. So this will be the eigenvalue of this a tilde matrix. Okay, or from equal to 0 we can find this characteristic equation. So this is s0, 0, s minus this a tilde matrix, this one we already computed. So 1 minus k1, 5 minus k2, 0, minus 1, and we just find this to be what? Okay, so the determinant of this will take. So this is s minus 1 plus k1. Okay, this is minus 5 plus k2, this is 0, this is s plus 1. Okay, and this determinant equal to 0. So the determinant is what? S minus 1 plus k1 times s plus 1 equal to 0. Okay, or just simplify that. So it will be s square plus s k1 plus k1 minus 1 equal to 0. So you can see that in the characteristic equation there is no effect of k2, right? Even though you have chosen k1 k equal to k1 k2, right? But here you see that only this k value, by choosing this k value we can place the eigenvalues of this matrix. Okay, so we want this to be what? This desired one, right? This red color box, whatever is in there, because we want our both closed loop pole to be at the 1 and minus 1, right? So this equal to this, then we see that k1 will be what? It will equal to 2, right? So now the question is that, okay, if we want other eigenvalue, we choose, okay, both eigenvalue to be different. Okay, for example, we want to choose this eigenvalue at the minus 2 both. Okay, so then what will be the characteristic equation? This characteristic equation will be what? So it will be s plus 2 whole square.
That's 1 2 whole square.
Yeah, so let's try this, s plus 2 whole square. So that means s square plus 4s plus 4 equal to 0, right? So then we see that, can we choose now by choosing k1, because we want k1 equal to 4 or k1 minus 1 equal to also 4. So it's not possible, right?
Yes.
Yeah, so you see why this problem is happening. So can you answer? So the answer is here. Okay, as you can see, it's not fully state controllable, right? We have computed this controllability matrix and we find that its determinant is 0. That means C is not of full rank. So that means also that you cannot choose your control to place arbitrarily or drive the state arbitrarily, right? All state. Okay, so that also clear from this decoupled equation, right? You see that x2 cannot be x2 dynamics is fixed, right? Here this x2 dot equal to x2 minus x2, you see that its dynamics fixed. So what is this eigenvalue associated with x2, this mode? So it's like x2 dot equal to minus x2. Okay, so this, let a this way, then x2 dot equal to ax2, right? So a is minus 1. So then this eigenvalue is what? So si minus a determinant equal to 0, right? For this one dimensional system, only x2. So it is what? S plus 1 equal to 0 or S equal to minus 1, or you can put also lambda per eigenvalue. Okay, so you see that it's only minus 1 and this is fixed, you cannot change, right? For x2 mode, can you change this dynamics? You cannot change, right? Because there is no effect of u there in the x2. Okay, so that is clear because of this decoupled. But if it is not decoupled, then you cannot directly say from this dynamics, so you have to check this countability matrix. Okay, so you see that is countability matrix is not full rank, that means there are some modes. Okay, so what is this rank of this matrix now? You said, can you answer what is the rank of C? So it's not full rank.
One.
Yeah, so full rank means it's not 2, so it's not equal to rank is not equal to 2, so rank of C is not equal to 2, but rank of C is 1. So rank also means how many independent column or rows are there. So you see that this is one independent row and that is actually repeated here, but one independent row is there already, so rank is 1. So rank 1 means there is one mode that you can control. Okay, the other mode you cannot control, it's not full rank. So if it's a n dimensional matrix C and let its rank is m, so rank of C is equal to m, which is less than n, then you can control m modes and you cannot control n minus m modes. Okay, so that means you can place your poles, m poles, at the desired location, that poles, that particular poles that are actually controlled by that control variable, right? And other n minus m modes that are not controllable, you cannot change them, they has to be there by this dynamics. For example, if this x2 dynamics, it is fixed whatever this model is there, because x2 mode is not controllable, right? So you see that actually reflected by this problem. So even though you have chosen a two-dimensional k1 and k2, this k2 effect is not there, and k1 only select, by k1 we can only select one variable. Okay, so once you fix this k1, then these two coefficients are fixed, right? Whatever k value you choose, this coefficient will be fixed. Only one mode of their freedom is there. So by choosing k1, you you choose k1 to match this value. Okay, for example, here we can choose either make this constant coefficient 4 or this coefficient with s equal to 4. You cannot make both them 4. Okay, so in this case what happens, because you have already chosen the other eigenvalue to minus 1, so you see that the other eigenvalue is minus 1. So you see that once you choose this k1 to be 2, this is actually already chosen by this 1, that is because you have chosen the other eigenvalue that is not controllable is minus 1, right? So you are just fixing that, you are not changing. But once you change both, you see that you cannot control. Okay, so what happens? Okay, now the question is, can I place the first eigenvalue say arbitrarily and the second one at the minus 1? Can I do that? Yeah, it is possible, right? For example, let choose first one as minus 2 and second one and minus 1. Then what will be the characteristic equation? So it will be s plus 2 into s plus 1. So it will be s square plus it will be 3s plus 2, right? Now you see that you can choose k1 to be 3 and this coefficient will be automatically 2, right?
Yes, sir.
So is it clear now?
Yes, sir.
Yeah, so it's actually depend how many modes are controllable. Okay, so in this case, in two-dimensional case, now you have two modes, and you see that your rank of this countability matrix that actually gives this information. So the rank of the countability matrix is 1. It is not full rank, that is it is not 2, but it's 1. So one mode you can control and other mode you cannot control. Okay, so the uncontrollable mode eigenvalue will be fixed there, whatever they are earlier, you cannot change them. Only this controllable part you can control. So if it is fully controllable, then you can choose arbitrarily for all these n eigenvalues, right, or n closed loop poles. So you see that for a general case, when this rank is something less than the full rank, only that person, that is that m number of modes you can choose. Okay, other modes you cannot choose. If it is full rank, that is it is n, then you can choose all these n eigenvalues arbitrarily. Okay, so then we move to next question. So Okay, so now you see that we are given a state space model here, so it's three-dimensional model, and it's already in the controllable canonical form. Sorry. So it's already in the controllable canonical form. So what happened in the controllable canonical form? So we'll see that the design process will be very easy. Okay, so we'll just see that. Okay, so now you see that you may have some desired steady state error, or you want some uh, what some uh, transient response or something, so that can always be translated into the pole location, right? So this is the desired pole location you want. So whatever you are given, this damping coefficient and this natural frequency, that always translate into this dominant poles. Okay, so now this issue is that in the frequency domain you can just place this dominant pole, right? You cannot place this third pole arbitrarily. Okay, if you just recollect in the frequency domain, because this frequency domain the data will be given in terms of zeta and omega n. Then using that data, you know that this plus minus j omega n 1 minus zeta square for undamped case, this is the dominant poles. Okay, you can just place the dominant poles, but in the state space model on the time domain you can place all these poles. Only condition you need that your system should be fully state controllable. Okay, so here we want to place these two poles, these dominant poles at this location, and the third pole at some distant location in the left plane. Okay, so then what we will do? So we want some feedback form such that this A matrix will have this eigenvalues or this pole at this desired location. Okay, so first we will write this characteristic equation first. Okay, so the characteristic equation for the desired location. Okay, so these poles are at what? So one is at this complex conjugate, that is the dominant poles, and other is this 10. So okay, so then you can write this 4 s plus 2 plus j4 s plus 10. So this will give this characteristic equation for the desired poles location. Okay, for this. So then we just simplify that. So this is just you can see that if you take a, then a minus b, a plus b, so this is s plus 2 whole square, a square minus b square, and this is minus j 4 square is what? So this is j square will be minus 1, so it will be minus 1 times 4 square, okay, into s plus 10 equal to s square, sorry, s square plus 4s plus 4, and this will be plus 16 times s plus 10 equal to 0, or reply that s square, you just simplify that, so it will be s square plus 4 4s, and this is 20. Okay, I just write this 20, so 4 plus 10 14 s square, so this is q plus 60s plus 200. Okay, so this is the characteristic equation of the with the desired pole location. Okay, so now we compute this, from direct method. What do we do? We just compute this closed loop matrix, that is the a minus bk, when we use u equal to minus kx. So this is the closed loop matrix. We compute that, we compute the characteristic equation associated with that, and we just make this coefficient equal each of this. Then we will find k1, k2 and k3 value. So so you see that, okay, so a minus bk, okay, so equal to a, but b is what? 0 0 1, so this is k1, k2, k3. So then it will what? A minus, you see that first element will be all 0, only last element this will reflect. Okay, because of this special form of this b. Okay, so this is because of this controllable canonical form. Okay, because b has 0 0 in the all this rows, only the last row is 1. So you see that it's this k effect will be only at last row only. Okay, so we can simply write now that whatever a matrix is there, it will remain the previous rows, only the last element will change, right? So it will be minus 1 plus k1. I'll write clearly. Okay, I'll here write. Okay, so this a minus bk, then what? You see that for a matrix only the last row will change, right? So first, right, this is 0 1 0 0 0 1. So this k2 k3 will subtracted from the last row only because of this b form. Okay, so it is minus 1 plus k1 minus what is 5 plus k2, and this is minus 6 plus k3, right? So this is the closed loop matrix. Okay, so you can now find the eigenvalue of this closed loop matrix, okay, by writing that Si minus of this matrix and taking the determinant equal to 0. But we also don't need to do that, okay, because we know that in the controllable canonical form, so for this controllable canonical form we know that what, okay, if you recollect in the controllable canonical form, okay, so if your characteristic equation is like this, let n minus 1 plus a n minus 2 and so on, a 1, okay, s plus a0 equal to 0, then the controllable canonical form, what will be this A matrix? You know that this will be all 0, then 0 0 1 and so on, all this. So last element will be what? It will be minus a0 minus a1 minus an, right? This coefficient will just appear in this, in the controllable canonical form. Okay, so but just observing this last row, we can directly write this characteristic equation, right? We don't have to use this Si minus a determinant equal to 0. Okay, is that clear? For this controllable canonical form, is this part clear? So
Yes, sir.
yeah, so in the controllable canonical form, these are the coefficient of this characteristic equation written in the reverse order. Okay, so for this, then what will be this characteristic equation? So it is third order equation, obviously, so it will be sq. So the coefficient with s square will be what? You see that this will be the coefficient, right? N minus 1. So this will be the,
6 plus k3 is
yeah, 6 plus k3 will be s square. This will be associated with s, and the last coefficient will be associated with the s to the power 0 or the constant term. So this is the characteristic equation. Okay, now we just compare this, because we want this to be exactly equal to this one, this red color box one, because this is our desired one. So we just compare this coefficient and we can easily find. Okay, so we want 1 plus k1 equal to 200. Okay, so I'll just write the desired one. So desired one is what? Sq plus 14 square plus 60s plus 200. Okay, we want exactly these two to match. So that means we just compare the coefficients. So that means k1 will be what? 1 plus k1 will be equal to 200. You know that k1 equal to 199. 5 plus k2 will be equal to 60. That means k2 will be 55. 6 plus k3 will be equal to 14. That means k3 will be equal to 8. So our k matrix is what? 199, 55, 8. Okay, so you see that the computation is easier when this matrix is, or the state space representation in the controllable canonical form. Okay, so actually it helps in the design process. Okay, so because it is in the controllable canonical form, so you don't have to do all this step, you just write this coefficient directly. Okay, because this k will add up only in the last row. You can directly write this characteristic equation, this one directly, right? And you can just compare with the desired one, and then you just get the this gain magnitude. Okay, so I already used that. Okay, so then we see that this one. Okay, so now we will use a different method to do that. Okay, So we'll use Ackermann's formula. So if you remember what is this Ackermann formula, so okay, this Ackermann formula is applicable only for fully state controllable matrix. Okay, so why? Okay, because it uses that formula. Okay, Ackermann formula is what? For n dimensional one, you use all this n minus 1 zeros, and the last one you put this 1. Okay, this matrix multiplied with this controllability matrix inverse. Okay, then this state transition matrix. Okay, this is the characteristic equation of the desired one. Okay, so this red color one, so this one, and you substitute a matrix, that is the original matrix A there, and you find that, so this will give this gain formula. Okay, so you see that C need to be invertible there to use this formula, right? So that means C determinant should not be equal to 0, or in other case rank of C should be what? Full n. So it's only applicable for fully controllable matrix. Okay, this Ackermann formula. Okay, so you have to remember that, because you need this C inverse, that is the controllability matrix inverse. So it's only applicable for this. Okay, so we'll use Ackermann's formula to compute this exactly the same problem. Okay, so solve this problem. Okay, so we just first find this controllable, first we check whether this is fully controllable or not. Okay, so for this C will be what? B A B A square B. Okay, so we can just compute. So I'll just directly write, because this you just have to multiply and compute. Okay, so B is what? 0 0 1. AB will be what? Okay, I'll just compute here. So B is 0 0 1. AB will be what? Then A is 0. Okay, 0 1 0 0 0 1. Last one is minus 1 minus 5 6. Okay, minus 1 minus 5 minus 6 into 0 0 1. Okay, so you see that only this last element will come, because other will multiply to 0. So you can directly write to be 0 1 and minus 6 this. Okay, then we compute A square and B. Okay, so the A square we compute, so A square, so okay, okay, so we'll just compute. So I have already computed, so I'll just write directly. Okay, or we can compute this A square and then, okay, so A square and B. So you just see that you just need this last column only. Okay, so that will come, so you can just verify and compute this. Okay, so this okay, okay, I will use calculator or something to compute this. Okay, so it's coming up 1 minus 6 31. Okay, you just can verify. So this just lengthy calculation only. So this is A square B. Then your controllability matrix is what? B is this 0 0 1 0 1 minus 6 1 minus 6 31. Okay, so this computation will be a little bit lengthy, because C inverse you have to also compute. So I'll just compute the C inverse. I'm just writing. You can verify using calculator also, or MATLAB. 0 1 0 0. Okay, so this is the C inverse. Okay, so okay, so we already have the C inverse matrix. Okay, so this is C. We computed to C 0 1 minus 6 1 minus 6 31. Okay, okay, so then we also need this characteristic equation, and we put A there. Okay, so what is this characteristic equation? So this is the desired one. Okay, so this one, so I'll write here. So phi of S is what? S cube plus 14 S square plus 60S plus 200. Okay, so this is the characteristic equation for the desired system. Okay, after placing these poles, so we already computed that one, right? This desired one. So this is the characteristic equation, and we will compute this phi of A. That means we will put A in place of S. Okay, so it will be AQ plus 14a square plus 60a, because we are adding matrix, so at the end also we have to multiply identity matrix, because it is a scalar, we have to make this vector. Okay, sorry, matrix. So you just compute that with using this A matrix. So A matrix is given as 0 1 0 0 0 1 minus 1 minus 5 minus 6. Okay, you substitute that and compute. Okay, again lengthy calculation, I'll just skip that, so you can compute this one. So I already computed that, so it is coming out to 11955 8 minus 8 159 7 minus 7 minus 43 minus 17. Okay, so once you have this, then you just use this Ackermann's formula. Okay, so k, this is k1 k2 k3, this is equal to, because the 3 dimension is 3, so 0 0 1 C inverse phi of A. Okay, so you see that this is 0 0 1 C inverse, that is the inverse of this conservative matrix. We computed this one 5 6 1 5 6 1 6 1 0 1 0 0. Okay, 1 0 0, and this one we also computed here. This is 199 55 8 minus 8 159 7 minus 7. So just computation, just algebraic computation, nothing else. Then you see that this is because in the last element, so you multiply this with this one, you see that only this element will come, right? So you can write it 1, if you multiply this with this row with this column 1, this with the second column 0, this one in the third column, this one, because this 0 0 will multiply with other element, so this and this matrix, and I don't care whatever in the end 55, because if I multiply this with this, only the first row will come out, right? So it is 199 55 8. Okay, so this is exactly what we obtained also earlier, right, using the direct method. Okay, you see that using that Ackermann's formula we are also getting the same result. Okay, so now we'll solve a simple problem just to illustrate other methods also. Okay, so this again, this ball placement problem we'll consider, but we'll see that how we can do like other methods. So we have seen two methods. One is direct method, so you just compare this desired characteristic equation with the your closed loop characteristic equation A minus bk, and just measure this coefficient to find that. So that is easier when it is in the controllable canonical form. If it's not, then it's you have to compare this coefficient. So for 2 cross 2 it's not be difficult, but higher dimension it will be little bit difficult. Okay, so the other method was Ackermann's formula. Okay, so in the third method, so it will be like transforming this system. So you have given any arbitrary state space representation, you transform it to the controllable canonical form. Then you already know that in the controllable canonical form the design is easy. Then you design your K matrix in that controllable canonical form, then you transfer back this K matrix to the original form. Okay, so we'll just see that gradually. Okay, so the steps, all the steps. Okay, so first we'll just do direct method here. Okay, so we are given this state system, and we want to find this controller design such that these poles are at -3 and -4. Okay, so the first thing will be what? So we'll check whether this system is fully controllable or not. Okay, if it is not fully controllable, then it's not possible to arbitrarily place this pole, right? So just first check that. Okay, so okay, so we'll see, first see. Okay, we will compute that. Okay, yeah, so this controllability matrix, so I'm denoting Cx. Okay, so I will just transform this to a z coordinate, so that's why I'm just denoting it to Cx. Okay, just to distinguish it. Okay, so it will be b a b, so b is already given 0 2, and ab will be what? So 1 1 minus 4 minus 3 multiplied with 0 2, and you see that it is 0 sorry, this will be 2 minus 6, right? So this will be equal to 0 2 2 minus 6. Okay, and this determinant of Cx is not equal to 0. Okay, it's -4, not equal to 0. So you see that its rank of Cx is 2, is full rank. So the system is fully controllable, so we can arbitrarily place our poles. Okay, so we'll proceed with the design now. So first we'll write the characteristic equation with this pole. Okay, so what is the desired characteristic equation? So we want this pole to be at 3, -3 and -4. So it will be s square plus 7s plus 12 equal to 0. So this is the desired characteristic equation. So we'll first use the direct approach. For direct approach, then we compute this a minus bk. Okay, a minus bk. What is this? A is given 1 1 minus 4 minus 3 minus b is 0 2 k1 k2. So it is 1 1 minus 4 minus 3 minus 0 0 2 k1 2 k2 are equal to 1 1 minus 4 minus 2 k1 minus 3 minus 2 k2. Okay, so then we find this a minus bk. Okay, the characteristic equation associated with this closed loop a minus bk matrix. Okay, that is si minus a equal to 0, or implies that s 0 0 s minus, this is a minus bk, this one. So this is 1 1 minus 4 minus 2k1 minus 3 minus 3 2. Okay, if some step are not clear, just interrupt and ask me. Okay, so I'm just assuming because these are just algebraic operations, so I'm just assuming it's clear. Okay, if not, you can interrupt, okay, and ask. Okay, so then we write this. So s minus 1 minus 1 4 plus 2k1, and this is s plus 3 plus 2k2. Okay, this is the matrix, and we take the determinant and equate it. So this will give the characteristic equation for the designed closed loop system. Okay, so simplify that. So this actually gives s minus 1 into s plus 3 plus 2k2 minus minus plus, so plus 4 plus 2k1 equal to 0. So it is s square plus 3 plus 2k2 s minus s minus 3 plus 2k2 plus 4 plus 2k1 equal to 0, or reply that is s square plus 2 okay, plus 2k2 s plus 1 plus 2 k1 minus k2 equal to 0. Okay, so this is the characteristic equation associated with the closed one when we use the gain k1 and k2. Okay, we want exactly this equal to this desired one. Okay, this red color one. So this is 7 and 12. Okay, this is s square plus 7s plus 12 equal to 0, the desired one. So this is the desired one. Then we just compare this coefficient. So we'll get 2 plus 2k2 equal to 7. So that means k2 equal to 5 by 2, and 1 plus 2 k1 minus k2 equal to 12. So like that k1 equal to so yeah, 11 by 2 plus k2 to 11 by 2 plus 5 by 2, so it is 8. Okay, so we get this k matrix 8 and 5 by 2. So this will place this gain will place our closed loop poles at -3 and -4. Okay, so it's okay. Now we see that, okay, we'll check using that Ackermann's formula also for this case. So we already computed C matrix, that is the controllable matrix, this one. So C x computed that, so it is 0 2 2 minus 6. Okay, 0 2 2 minus 6. So we need C x inverse. So this is determinant is minus 4, this is minus 6, 0, minus 2, minus 2, it is 3 by 2, half, half, 0. Okay, so this is C inverse, Cx inverse. So this is just adjoint of C by determinant of that. Okay, determinant is minus 4, adjoint is this one. So then we need this characteristic equation. So this is this characteristic equation. This is phi s is equal to s square plus dz1. This is 12. So we will compute this with this A matrix. So this is s square 7. Okay, A matrix. So we have compute s square plus 7a plus 12i. Okay, so this you can check and compute. So I already computed that. So it is 16 5 minus 20. So you can use calculator or MATLAB to compute that, or you can easily compute for 2 plus 2 matrix. That's not difficult. So in this Ackermann formula, then what? So it's actually K will be what? Then 0 1 Cx inverse. This is phi a 0 1 Cx inverse. So we computed this 3 by 2 half and 0, right? Okay, and this is 16 5 minus 20 minus 4. So it's this multiply with this, so it will be half this 0, right? 16 5 minus 20 minus 4, so it will be half into 16 8. This is 5 by 2. Okay, so this is exactly what we obtain also in the direct method. Okay, so then we move to next question, next method, that is we transform into the controllable canonical form and design there in the controllable canonical form, and then we obtain this K matrix if the system is given in the controllable canonical form. Okay, then we transfer back this K matrix to the original one. Okay, so this will be easier when I will just explain the steps for this problem. Okay, so first thing is that, okay, so this is actually given this in the this form. Okay, so this is not in the controllable canonical form. So what will be this controllable canonical form for this then? Okay, so let this is given in the z dot equal to a tilde z plus b tilde u. Okay, so this is where this A matrix is in the controllable canonical form. So that means this will be like this. Okay, so first we write this characteristic equation. So if it is a1s plus a2 a0 equal to 0. Okay, so for this A matrix, then this controllable canonical form will be what? This one, right? This will be a tilde and b will be 0 1, right? So you can easily write this in the controllable canonical form. Okay, so first then we find this characteristic equation for this A matrix. Okay, not the desired one, because we want to find this controllable canonical form for this one without design. Okay, is that clear? This controllable canonical form. Okay, so first we write the characteristic equation for this A matrix. Okay, without this design. So it will be minus 4 minus 3. So it is equal to s minus 1 minus 1 0 s, sorry, 4 s plus 3 equal to 0. So we have s minus 1 s plus 3 plus 4 equal to 0. This is s square plus 2s minus 3 plus 4 equal to s square plus 2s plus 1 equal to 0. Okay, so this is the characteristic equation associated with this A matrix. Okay, so you see that this a1 is this one 2 and a0 is 1. So what will be the controllable canonical form then? This will be 0 1 minus 1 minus 2 z plus 0 1 u. Okay, so is it clear how we got this controllable canonical form? Okay, I am just using z because not to confuse with x. Okay, so we transform this. Okay, is it clear or should I repeat?
Yes, yes.
Should I repeat or clear?
No, sir.
Clear, right? Okay. So so this is in the controllable canonical form. So you can write controllable canonical form once we have this characteristic equation. So you know that this coefficient will appear in the reverse order with the negative sign, and this is the B matrix. So this is the A tilde, this is the B tilde, because we want of this form. Okay, this form. Okay. So now it is in the controllable canonical form. So the design will be easier, right? Okay. So before that. We'll just find the P matrix that can transform this into a controllable canonical form. Okay, so we just manually obtain. So, so the question will be: is there any matrix E that actually transforms this? Okay, so the original system is given in this form, arbitrary form any. We want to find a desired form. Okay, so here the desired form is this controllable canonical form. Okay, it can be any desired form. Okay, that is valid for any desired form. So how can we transform from this to this? Okay, we did it manually, but is it possible to transform from this to this without uh, manually? Is there any matrix P such that we can have this form x equal to pz? If we substitute in place of x this pz matrix, so will it transform to this desired form? Okay, so this desired form can be any form. Okay, so we require only controllable canonical form, but it can be transformed into any form. So this is called similarity transformation in the matrix. Okay, in the matrix case, in the matrix analysis, it is called similarity transformation. That is, you are given uh, this ODE in one form. This is x dot equal to ax plus bu, because you already know that your state space representation is not unique, right? So you can write your state space representation in any form. So you have already seen diagonal form, controllable canonical form, observable form, and so on, but it actually represents the same system. Okay, so your state space representation is not unique. So the question is, you are given a state space representation in one form, can you transform into any desired form? Okay, so this desired form in our case is the controllable canonical form. Okay, so just for now assume that okay, there exists one transformation that can transform this, and we will see that how this P matrix is defined then. Okay, so the, okay, so we are given in this form, that is x dot equal to x plus bu, one form. So this x is any n dimensional matrix. Okay, so this is for valid for any n cross n matrix or n dimensional state space representation. Okay, we want to transform it to another form, this form. Okay, so we use this transformation x equal to pz. Okay, so just substitute this one in this equation and see what we are obtaining. So x dot will be what then? X dot equal to will be pz dot, because p is a coefficient matrix. Okay, it's not dependent on the time. So we just put this in the first equation, this, so it will be pz dot equal to a x equal to, we can put pz, so pz plus bu. Now okay, if p is invertible, okay, so p inverse exists, that means p determinant is not equal to 0 or p is invertible, then we can multiply p inverse on the both side, so it will be p. Okay, yeah, any doubt? Okay, voice, okay, can you hear, or I'm audible or not now?
No audible, sir. Before that, not audible,
Oh,
sir.
okay,
Some
okay,
disturbances.
okay, so I'll repeat that. Okay, anyway, no problem. So
Yes.
I'll repeat again. So okay, what do we want? We want to use this transformation x dot x equal to p a z, and we want to transform this form, and we see how this a tilde and a b tilde and b matrix are related. Okay, and also in that process we will compute this p matrix. Okay, once we are given, okay, so two cases is there. We are given this p matrix, then we can find this a tilde and b tilde, and another case will be, we want a tilde and b tilde, our desired one, can we compute this p matrix? Okay, these two cases we'll see. So we'll use this transformation x equal to pz, for example, then x dot equal to pz dot, because p is a coefficient matrix, it does not depend on time. So then we just substitute this in this first equation, so it will be p z dot equal to a, in the place of x we can write p z plus b u. Now we assume that p matrix is invertible. Okay, so p is invertible, then p inverse exists. Okay, so this is also I will explain why we need p inverse also. So we just multiply p inverse on the both side, so it will be what, p inverse a p z plus p inverse b u. You see that you have z dot equal to p inverse a p z plus p inverse b u. So you can now compare this with the dz form, and you see that this is a tilde and this is b tilde. Okay, so a tilde is what, p inverse a p, and b tilde is p inverse b. Okay, so this is one way. So you are given p matrix, then you can find the transform form z dot equal to this a tilde b tilde, where this a tilde and b tilde will be related to the original matrix by this form. Okay, so now assume that we want dz1. In our case we want this a and b tilde dz1, right, this controllable canonical form. So can we come up with a p matrix that will transform that? Okay, so why we are doing also, it will be clear when we go to design process, because we will need this p matrix. Okay, so now, okay, you are given this form ax plus bu and z dot equal to a tilde z plus b tilde u. Okay, now we want to find this p matrix such that we have this transformation. Okay, so first write this controllable matrix for this. What is this controllable matrix? B a b up to this, right, for n dimensional case, a to power n minus 1 b. And for this controllability matrix will be what, b tilde a tilde b tilde up to a tilde to the power n minus 1 b tilde. Okay, but we can substitute b tilde this one, right, because if some p exists, then b tilde a tilde will be related by this one. Okay, so that means b will be p inverse b, a will be what, p inverse a p, so p inverse a p, b tilde is again p inverse b, and so on. So you can check this a to power n minus 1 will be what, so it will be a p inverse to the power n minus 1 p inverse b. Okay, then we see that it is p inverse b. So this p inverse will be identity, so it will be p inverse a b, and you can check also other also, the middle one always will cancel out. Okay, so we will left with p inverse a to the power n minus 1 b. Okay, so you can easily check that also by expanding that. For example, a tilde square will be what, so p inverse a p square equal to p inverse a p, again multiplied with p inverse a p. Okay, or this is a tilde, right, so a tilde is this, a tilde is this, so this p will cancel out, so it will be p a square p. And similarly a tilde n will be what, p inverse a n minus 1 p. Okay, so you see that this will come out this, or p inverse you can take common, so it will be b a b a to the power n minus 1 b. Okay, so what is this one, right, so is equal to p inverse cx. So what relation we get then, cz equal to p inverse cx. So you can compute p now what, so it is cx into cz inverse. Okay, so is it clear how you can compute this p matrix? Okay, so for our case, then for this two-dimensional case, okay, so we already computed this c controllable matrix, right, for the original one cx. Okay, so I'll write this. So cx we have in the x domain, the controllability matrix was 0 to 2 minus 6. Okay. 0 to 2 minus 6. Okay, now in the transform domain cz, we will compute this controllability matrix. Okay, so in the transform domain where we have this z form, I have written that. Okay, So this is the okay, original one. We then transform this, okay, in the controllable canonical form. Okay, this one. Okay, this one. So for this, then what will be the CZ matrix, this controllable matrix for this? Again we have B tilde and A tilde, B tilde, right? This will be B tilde is 0 1, and if you multiply A tilde B tilde, it will be this one 1, this is minus 2. So this is CZ. Okay, so CZ is 0 1 1 minus 2. Okay, so in the Z domain minus 2. Okay, so then we will find this P matrix, the matrix that will transform from our given in the X domain to the controllable canonical form that is represented by the Z domain will be what? This P matrix will be by this formula Cx into Cz inverse. Okay, so just compute this Cz inverse. So the determinant is minus 1, this is minus 2, 0, minus 1, minus 1, it is equal to 2, 1, 1, 0. Okay, so you see that this is 0, 2, 2, minus 6 multiplied with 2, 1, 1, 0. So you have 2, 0, minus 2, 2. Okay, so this P matrix, you see that will transform from the X to Z domain. Okay, so now I come to the question, why we need this P to be invertible. Okay, so you see that, so one way we are converting from X to Z, then the question will be whether you can convert from Z to X or not. Okay, so whether this conversion is actually unique or not. Okay, so can you answer when will be this conversion will be like exactly 1 to 1 correspondence, or you can convert from one to other and other to one? Then the question will be there should not be any data loss, right? So when we multiply with this P matrix, there should not be any data loss, or should not be any information loss. So that is only possible when this P is actually full rank. So it is actually related to the matrix analysis also, so I will not go to in detail, but you see that in this case, when we are multiplying with P and P inverse, then only we are getting that Z form, right? Otherwise that is only we are getting PZ. Okay, so it is possible that P not be a full rank, then this is not, we cannot get Z directly. Okay, so for that we need P inverse. So it is actually related to rank and nullity, so I will not go to that detail. But for similarity transform to exist, unique transformation, that is you can transfer from X to Z and also in the reverse, and you can always get back to the original one, then that transformation matrix need to be invertible. Okay, so we have this P matrix now, so this P matrix will transfer from the X to Z domain. Okay, so now we'll design in the controllable canonical form. So in the controllable canonical form, the design is very easy. Okay, so this characteristic equation we'll write. So the desired characteristic equation we already have that. So this one, x square plus 7s plus 12. Okay, so this is the desired one, and from the controllable canonical form you can easily guess this A tilde minus B tilde K, I am denoting with KZ. Okay, so distinguished from the original one in the X domain. So this will be what? This matrix will be 0 1 minus 1 plus K1. Okay, KZ1. Okay, so I will just KZ1, and this is minus 2 plus KZ2. Right? Is it clear? Because B matrix is this one, so when we B tilde into this KZ1, KZ2, you see that this is B matrix and this is 0 1 KZ1, KZ2. So you see that only the last element will appear, right? Other will be 0, and this will be subtracted from this coefficient. So in the controllable canonical form, without even doing this, we can directly write from this, right? You see that here only this K1 and K2 coefficient will come. Okay, And then you see that these are the coefficient of the characteristic equation also in the controllable canonical form. So what will be this? It's 2 plus this first element s plus 1 plus k. Okay, so is it clear? This is direct, right? Okay, so then this will be what? Just comparing this equal to this and this coefficient equal to this. So the first element will be what? 11. Second will be 2 plus this equal to 7. So this is 5. Okay, kz. So we have obtained this kz in the controllable canonical form. Okay, but we want this kx in the original one. Okay, this in the x domain. So how will you obtain this? Okay, so we'll see that also. For general case, we'll see that this is the formula, so we'll derive that also and see how we are obtaining. Okay, so in the original case we have a minus b kx x, right? In the controllable canonical form we design it to be this b tilde kz. We design kz now, so this, and we want to find the relation between the kx and kz. Okay, so what we will do, because we already computed a tilde to be p inverse ap, b tilde is equal to p inverse p. Okay, p inverse b. So we substitute that here. So it will be z dot equal to p inverse ap minus p inverse b kz into z. Okay, but we know that x equal to what? Pz, right? So we just substitute that also on the both side. So it will be p x dot equal to p inverse ap. Sorry, no mistake. Let's check. Okay, yeah. Sorry, yeah. So this will be, yeah. Then p is invertible, that means z equal to p inverse x, right? So it will be p inverse x dot. Okay, so this is minus p inverse b kz, and z is again I can write p inverse x. Okay, so I'll write p inverse, I will take common, so it will be a minus b, okay, p b kz p inverse x. Okay, so p inverse on the both side it will cancel, so it will have x dot equal to ap minus b kz into p inverse x. Okay, but we want of this form, so what we can do, I can write this also like this, b kz p inverse p. I can take, I just multiply this p inverse p because this is identity, this, and you see that I can take p common from both, so it is b kz p inverse p times p inverse x equal to a minus b kz p inverse x, right? So we compare this with the original one, this one, so it is equal to then what? A minus b kx x. So from that you can easily see what is this kx, then kz into p inverse, right? You can just compare this red color ones. So this is just, so once we design in the controllable canonical form, we can easily obtain this in the given form if we just multiply is with the post multiplied with the p inverse. Okay, so we'll do that thing. So that is also mentioned here. So this is this relation. So we have kz, this one. Okay, so p we already computed. Okay, so we just compute p. In the previous we computed this p, right? So what similarity transformation this p matrix will give? So this is 2 0 minus 2 2 0 minus 2 2. Okay, so we need p inverse, so we compute this p inverse. So the determinant is 4, this will be 2 2, this is 2 0, so it will be half 0 half half. Okay, p inverse. So then okay, so then we know this kx is what? This is kz into p inverse, right? and kz we computed in the controllable canonical form 11 5 11 5, and p inverse is half 0 half half. Okay, so then we see that this is what this multiplies this, so 11 by half plus 5 by half, this is this, so 5 by half, and this is 8 5 by half. So this is what we already obtained, right, in the original design, as you can see here, this one. So yeah, so we just denote in the kx because we design in the x domain. Okay, so I'll just explain this step again simply. Okay, so what we did, okay, so just to recollect the steps, what we do, we are given in the x domain, okay, sorry, x domain x plus bu some form that is not in the controllable canonical form. Okay, so this for two dimension it is easy to design in any form, but in the higher dimension it will be difficult in designing in the arbitrary domain, like arbitrary given form. So what we will do, we transform into controllable canonical form, which is denoted by z, a tilde z plus b tilde u. Okay, so we use this transformation to transform that from the given form to any given form to controllable canonical form. We design in the controllable canonical form. Okay, so how to find this p matrix? So p matrix will be cx into cz inverse, where c is the controllability matrix in the x domain and cz is the controllability matrix in the z domain, and a tilde is related to a by p inverse a p, and b tilde is related to p inverse b. Okay, so from using that we obtain this relation p similarity transformation, and we obtain this p matrix. Okay, so now we have this in controllable canonical form, that is also easily obtained by just writing the characteristic equation, controllable canonical form. Okay, so we design in the controllable canonical form the controller design, that is actually easier, and we obtain that kz matrix, and we want to find this kx matrix in the original case. So how this is related? We obtain that kx equal to kz into p inverse. So p is this matrix, or I can directly also write this formula here, kx equal to what, then kz cx cz inverse. Okay, on this right here. Okay, what is this formula then? Directly, because we know that kx equal to kz p inverse, right, but p is equal to cx cz inverse, so kz into cx cz inverse. Okay, so this is how we obtain this in any given form. So you are given in the x domain in any form, in the any representation of this test space. You know that for higher dimension the design will be not trivial in that case by direct method, so you transfer it to the controllable canonical form. So the transformation can be easily obtained this by p matrix, by writing this controllability matrix in both cases. Then you design in the controllable canonical form. So you have already seen that in the controllable canonical form it is easy to design. You just compare this last row and you obtain this k matrix, this feedback gain matrix in the controllable canonical form. This is kz matrix. Then you transform back into the original kx matrix, that is the gain matrix in the x domain, by using this formula. Okay, so this is the third method you can use. Okay, for higher dimension it will be easier to compute this, or using MATLAB also. Okay, so that I just explained it using the 2x2 matrix just for simplicity. Okay, so is it clear, or any doubt you have? Okay, so if no doubt, then okay, we can stop there. Okay, so okay, I'm stopping this recording also.